So it's still 2 minutes. So, hello everyone, and welcome to today's webinar, Printed Electrochromics. It's the first webinar in a series that Ynvisible will launch under the hashtag Things Alive. My name is Tommy Höglund, and I'm the Vice President for Sales and Marketing for Ynvisible since November last year. And I will be your moderator today and guiding you through this webinar. Before I started at Ynvisible, I have been working almost 10 years in the field of printed electronics with business development as the manager for an innovation cluster called the Printed Electronics Arena at the Swedish Research Institute, RISE. And I'm very happy and excited to be sharing this session today with you. We have exciting speakers that will present really astonishing achievements in R&D and also in real products. And I'm also very happy to be here with our great audience. We actually have over 170 registered attendees for this webinar today. And I would like to start already now to say thank you for taking your time and being here and sharing this webinar and creating this webinar together with us. Before we jump into the presentations, I would like to start by saying a few words about Ynvisible. And Ynvisible is a publicly traded company listed in the Toronto Stock Exchange venture list. And being a listed company, we like to underline that today's presentation contains certain forward-looking information and statements about Ynvisible. We at Ynvisible develops and brings to market printed electrochromic displays that are low power, lightweight, thin, flexible, transparent, and robust. And our business model allows us to help companies to make electrochromic displays no matter at what maturity stage they are. We can help you from idea to design and prototyping and all the way to high volume production, and even help you to licensing the Ynvisible display technology and inks to your own or to a third-party production. In addition to high volume production of electrochromic displays, we also have very high capacity in our production line that is right here behind me, that we utilize for doing printed electronic components and systems for other companies as well. And I'm pleased to share the agenda with you and the speakers of today. First out, we'll have Carlos Pinheiro, CTO of Ynvisible, followed by Anna Österholm, Senior Research Scientist at Georgia Institute of Technology. And then we'll have John Coyne, CEO of NXN-IP. And last, we will also hear from Ashley Colley, with PhD in Creative Technologies at University of Lapland. And they're gonna share their experience and deep insights into how to make things alive using electrochromics. And this will help us to understand and see the opportunities using this technology. But before we jump into the presentations, I just like to go through a few items that is important for us in this webinar. The first thing I want to state is that today's webinar will be recorded and available on demand. And you will find it if you follow us on our social media. And you can find it on Facebook, Twitter, LinkedIn, and our YouTube channel as well. So please subscribe to our social media channels. And at the end of this webinar, we'll be running a live question and answers. So we have enabled a Ask a Question feature. It is at the bottom of your screen. So if you have any question, just pop them in. And if you have any questions after the webinar, there will be a survey after the webinar where you can send comments and questions and request also more information from Ynvisible, NXN, Georgia Tech, and the University of Lapland. So without any further ado, I would like to welcome today's first speaker, Carlos Pinheiro. And Carlos is Ynvisible's CTO, and Carlos's PhD was a very crucial piece in the development of Ynvisible's electrochromic display technology. And today, Carlos is responsible for the technical content of Ynvisible's patent portfolio, and he also leads all the scientific and technical activities and development within Ynvisible. So with these words, I'd like to welcome Carlos and hand over to you.
Thank you, Tommy. Thank you, everyone around the world, for joining this webinar. It's a very impressive number of participants. I will start by sharing my screen. In the next 10 minutes, we'll make you a tour through the world of electrochromics. And in particular, I want to highlight a specific area of electrochromics, which is printed electrochromics. First of all, as a reference, you may have seen in your daily lives applications of electrochromics. Most of these applications today are used to dim light. They have been used in smart windows, in architecture, or for airplanes. The most recent Boeing airplanes, they are all equipped with electrochromic windows. There's no more shades as before they were. And also in most of the motor vehicles today, they are equipped with a mirror, a dimming rear view mirror. That it's one of the best commercial success examples that we have today in electrochromics. It's been used in more than 100 million motor vehicles worldwide, and Gentex, which is the company that developed this technology, has a production capacity today of 700,000 units per week of this technology. And as a side note, the chemist behind this technology at Gentex, Alan Biker, he in the 80s developed this very brilliant and perfect electrochromic system that allow us to have this comfort of dimming the reflection of light in the rearview mirror in cars. And I'm pleased to tell you that Alan has joined our advisory board in 2018. So it's a very welcome guidance we have in our advisory boards. Now, jumping to the basics and the science of behind the electrochromics, how is this color change obtained? And I brought here a little bit of chemistry, very simple chemistry and chemical reaction, and also a scheme of an electrochromic device. All starts with a very special set of materials which are called electrochromics, and these materials have the property to show different color properties or optical properties according to their oxidation states. And so we are dealing here with a system whereby tuning the redox state of a certain specific compound, we can tune the color we see. As you can see on the right side, I don't know if you see my pointer. On the right side, we have the electrochromic layer in the device that will perform the color change according to the oxidation states. To perform that oxidation state, we need to inject or extract electrons out of the material. And for that, we need an electrical circuit, which is here demonstrated, which will allow us to control the exact ratio of oxidation and reduction of the material. And by that, we are tuning the color. And finally, in order to get a properly working system, we need to balance these charges that are being accumulated on the surface of the electrodes. And that's the main function of an electrolyte material that you see here in yellow that is between the two electrodes. It's a bit simplified. We have here on the left side of the device a counter electrode. This is also to balance the electrical charge. And so we basically have to respect these basic compensation rules. One is electrical compensation, the other is ionic compensation. And if we have all these pieces together, we can create an electrochromic device that will switch between two color states reversibly upon the demand of the user. It's important to highlight that this is a technology which is not dependent on environmental factors. So it's not a system that reacts upon light or upon temperature. So it's only reacting to electricity, which allow us then to command when do we want to see this color change. Coming back to glass panel and glass technology, it is a great starting point, but this is not where we are going as Ynvisible. We are looking to all the learnings that has been done in this field, which is a huge market, it's a huge application, and it has a very noble purpose to save energy consumption in buildings. But we want to expand the applications and the possibilities with electrochromics. And we are moving from the techniques, physical deposition techniques and substrates like glass, into printing techniques, printing electrochromic materials, and using flexible and transparent substrates so that we can build a new product based on the same technology, but with a different form factor, which is a printed electrochromic display. Where do we find uses for this new function, which is low-end information printed display? If we consider these two information extreme technologies, on one side you have static printed graphics, which is an ubiquitous technology around us that has been for centuries with us. And on the other edge, we have high resolution displays like the ones we have in our smartphones. In between these two worlds, there's a gap that hasn't been properly assessed by any technology. And this is where we we are developing concepts and solutions to empower the already existing printed graphics technology and to make it more functional by having dynamic dots. Sorry. All right. Doesn't work. So instead of having standing still dots, we can now, with electrochromics, we can have dots that can change the color. And so by just this very small and slight color change, we can bring new functions into a wide range of applications and products based on static printed graphics. As an example here in this video, this is a product we have delivered to an airline company. This was a boarding pass to announce a campaign price they had, and they were looking for something else that would capture the attention of the user and make this a memorable event so that they could remember this advertising. And here you have an example how we can convert something that is typically static into a dynamic information. And this is only one example. We are working in other applications that you can see here. I will not go into the details. There will be in the next webinars more information about this. But basically what we are bringing here is a new and disrupting way to display information in order to provide practical human interface to smart objects and ambient intelligence. Meaning this, that objects are getting more and more intelligent. There is electronics embedded in objects that we even don't know they are there. And we are bringing the visual element that will allow these electronics to easily and friendly communicate with humans. And why electrochromics? Why not other technologies like electrophoretics or liquid crystals? Well, I will go now through some slides that will show you why there hasn't been an attempt before to bridge this gap between static printing and high-end displays. And these are some of the features that electrochromics can supply that others are not able. First, it's made of thin, flexible, and transparent substrates. It has a very low power consumption, and as well, it's driven by a very low voltage. It is a very reliable and robust technology. It can be punctured, it can be teared apart. As long as you still have the contacts, it will still perform its function. And it operates on a wide range of temperatures, over 100 degrees Celsius and below minus 100 degrees Celsius. And of course, this is very important for applications like cold chain monitoring or outdoor applications. Once we are printing and using flexible materials, we are not restricted to square displays, but we can have a free form factor that allow us to create and innovate with electrochromics. So in summary, we have developed reversible color change display technology that is used in our product Templable that can refresh the message multiple times. So we can write and erase and write again thousands of times. And most recently, we have developed also a fully irreversible electrochromic system where we can lock the color and keep it permanently and forever in a certain state without needing any power or any electronics. And this is our irreversible one-time use electrochromic displays. Looking beyond, and just to say that this is only the beginning, we are also continuing to develop new features like having new colors. And Anna Österholm will talk about this new set of materials that can allow new colors in displays. We're also working with a wide range of partners like VTT in the Decochrome project, where we are experimenting on overmolding electrochromics and hybrid electronic systems. And also in another big consortium in paper, together with the company Arjo Wiggins, we have proved that we can build displays out of paper together with printed antennas, and we can power the full device by just harvesting wireless energy from a smartphone. So we are, within all these initiatives, bringing and creating the platform for printed electrochromics by innovation in chemistry, delivering ink sets to allow people to get hands-on experience by themselves and learn how to use electrochromics. We are developing electrochromic design tools so that the barrier, the entry barrier is low for people that are not technology informed or they don't have a background as scientist or engineer. And also we are building the tools to have quality control. So the aim is to really empower and allow industries and markets to adopt and use and produce electrochromics. However, today we can already help you through the process, prototyping, consulting services, printed and high volume manufacturing of displays and other printed electronics. And also we can custom, if the available technologies or chemistries are not fit for your purpose, we can also help to develop these chemistries to your specific needs. And to say that all I have talked and all we have developed is not a single effort of our own company. We have been cooperating through the years with many companies, institutes, universities, and this list is expanding on a daily basis, and very soon we will be announcing more partners in this list. And that's all for now. Thank you, Tommy.
Thank you, Carlos. A great overview of the possibilities. Questions will be, as I said before, at the end of this webinar, where all the speakers of today will help to answer your questions. So, our next speaker today is Anna Österholm. She is a PhD, Senior Research Scientist at Georgia Institute of Technology, and she will talk about expanding the electrochromic color palette. And Anna has been doing research on electroactive polymers for over 15 years. And she has been working for Georgia Institute of Technology since 2012. Anna and her colleagues have been leading the development of electrochromic color palette and we are thrilled to hear more about this development. So over to you, Anna.
Okay, thank you, Tommy, for that introduction. I'm gonna see if I'm gonna wave to everyone. So good afternoon to everyone that is to the east of Atlanta, and good morning to all of you on the West Coast. I'm very excited to be here today that I got the invitation from Tommy and his colleagues to share a little bit about the research that we're doing at Georgia Tech and in the area of expanding the color palette of electrochromic polymers. And that's what I'm going to be talking about today here as I pull up my screen for you. So the goal of my presentation today is to give a little bit of scientific background into how we're planning on expanding this color palette and some of the design rules that we use to bring some more color into this field. So without further ado then, I'm also going to give my sort of take on the background here and sort of what we think about when we're designing colors. And if we think about what an electrochromic device actually is, it's simply a dynamic color filter. And that's what the cartoon is showing here for on the bottom here, then the electrochromic device here on the left that you can see here. And so the way a color filter works is that it contains a material that will absorb very specific wavelengths of light. And so in the example that I'm showing here, where we have this magenta filter, it's a filter that absorbs specifically green light and lets blue and red light through it. And so then when we're the observer looking at this filter, we're looking at this electrochromic device then, we're only gonna see a mixture of the blue and the red light coming through the filter. And so our eye is gonna observe it as being this sort of pink or purple color. And so really what we're doing at Georgia Tech then is designing molecules where we control what wavelengths of light that they absorb and what wavelengths of light that they transmit. Now, the difference then in our case, when we have this technology, as I said, it's a dynamic device, which is what Carlo just gave an excellent overview of. And so we can actually then also turn this color filter off. I'm going to take these off too. And what happens when we, as Carlos mentioned then, these are coupled to a power source, they're electrically driven. And so as we're powering this device then, what happens to the materials we design that are inside here is that we begin removing electrons from our electrochromic material. And in our case, it does a lot of different things to our material, but one thing that it does is that it changes the conformation of the the molecule or the electrochromic material. And that's why what I'm showing here on the bottom with these this schematic of this spring here. So what we can imagine is that when our polymer or our electrochromic material is in the colored state where it's absorbing light, we have a spring that's coiled. And it's coiled in a very specific way, which means that it's absorbing the green light and letting the blue and the red light pass through it. But then when we begin removing electrons, what happens is that we're changing the conformation. And so in our case, we're uncoiling this spring. And at Georgia Tech, what we are doing then is we're making the second conformation such that it transmits all visible light. So now we can have all the wavelengths going through, which means our eyes will see it as a transmissive or clear device. Carlos also highlighted a lot of the examples. This is certainly not a new technology. You can find it in cars and in the Boeing Dreamliner and multiple buildings across the US, one of which is on Georgia Tech campus. But what we're really trying to do at Tech is to bring some color into this field, because as you can see here, there's a lot of blue happening. And so we think that we have an excellent way to expand the color palette. And the way we do that, or the way we're proposing to do it, is to use electrochromic polymers. And there's multiple reasons why we're interested in using polymers specifically, but one of them is that we have exceptional color control. So there's a lot of synthetic flexibility that we have to tune the color of these materials. We're also working hard on making them soluble so that we can make inks. It's a thin film technology, and there's some advantages to that. One of them being that we can make them switch fairly rapidly, which I hope you can see on the bottom here, which was one of our little demo device we made a long time ago now, that switches from purple to clear, and you can see it switching. I think that's 1/4 of a second switch there on the right-hand side. Okay, so why are we using polymers? Well, polymers are large molecules. This is just a schematic showing a polymer. It's not what our materials look like specifically, but they have the similarity that they are large molecules. And that means that there's a lot of parts on this molecule that we can change out. And in that way, change how this material interacts with light. And so, for example, if we're looking to make a small color change, we could imagine doing something very simple. We could maybe take the green balls here and replace them with red balls. Now, if you look at the molecule as a whole, this is a fairly small change. We've only changed three balls there. And as a result, the color change that we observe then is going to be subtle. And to me, a subtle color change would be, for instance, having a material that's vibrantly yellow and can switch to clear, to changing the conformation of the molecule to make it appear orange. Now, sometimes, obviously, we might want to make a much larger color change than this. And then we have to look back on our molecule and make, obviously, a much larger change to the structure. And so then it usually isn't enough to just change a small part of the molecule. We're going to have to do something a little bit more drastic here. And so, for example, one thing we could do is to take the polymer backbone itself and actually take out every other gray ball and make that a green ball instead. So now it's a new molecule. And then we're going to see a much larger color change. So in this case, an example would be that we start off with something that's yellow to clear, and by changing out some of these, every other unit, we're going to have something that's now cyan to clear. So a completely different color. And this is something that we've done at Georgia Tech over many years now. And this is just one example that you see on the top of one of our electrochromic rainbows that we've developed. And so you can see, using this strategy of just changing how it's coiled and how these molecules interact with light, we've been able to create a huge number of colors. Now, what's really cool, in my opinion, with our approach is that if you look more closely at the structures, which I'm showing there on the bottom, beneath all these photographs, if you look at these, you're going to see something that they all have in common, and that is this dioxythiophene core, and that's what I'm showing here on the bottom left. So you will see this motif throughout all these polymers. Now, why is that nice? Well, it means that we're using very similar building blocks to build these large molecules, and so it makes our synthesis modular. And what do I mean by that? Well, it means that we can use very similar recipes to make all these different colors. We can use very similar reaction conditions. We can use similar purification methods when we make these different colors. And that makes the synthesis fairly straightforward, and it also makes it scalable. And what I mean by scalable is that the recipes that we develop at Georgia Tech, and when we're making materials, we might make them on a very small scale, something like a gram. But if your synthesis is scalable, it means that you should be able to give your recipe to a company then. They should be able to recreate these materials and have them perform exactly the same way, but make much larger batches of them. And that's very important if we want to move this technology ahead. As I mentioned briefly there earlier on, is that we can make inks. And so we worked over the last few years, especially at Georgia Tech, very hard on really optimizing and enhancing solubility of these large molecules. And the reason we're doing that is because if we can make these large molecules soluble, we can make electrochromic inks. And if you can make electrochromic inks, you can start printing these things or using coding methods that are available in the industry already. And so here are some examples of different coding methods you could use for these polymers that we've designed. So you could just go to the art store and buy an airbrush spray gun. You can spray them. You might use an inkjet printer, or you might do something a little bit more fancy that most of us don't have at home, which is, for example, slot die coating. And by optimizing and making sure these polymers are very soluble, they will be compatible with all of these different coating methods, which is really pretty cool, I think. Another thing that's pretty interesting and neat with these materials is that you need very little of a material to make get a very vibrant color. So what you can see here in this slot die coated thin film here, that's on the order of 200 to 300 nanometers thick. So it's a very, very thin film, yet the color is really vibrant. And what that means is that you need very, very little material to actually make large area coatings. And so my colleague recently did the back of the envelope calculation and came to the conclusion that if we would make electrochromic coatings on every single window in the Empire State Building, it would only take 20 pounds of one of these polymers. And in my opinion, 20 pounds isn't that much. It's like, I guess, 9 kilos. So really something that we don't need a lot of material to make, to get pretty colors. Another thing that's pretty neat when you have something that's an ink and that's soluble is that you don't necessarily have to make a new color every time you want a very specific hue. We can just mix colors together, which is what I'm showing on the bottom, just like you would mix paint or watercolors. And so one student was interested in recreating Coke Red. The reason being that the Coca-Cola headquarters is Georgia Tech's neighbors. That was one of the reasons we did that. But we measured we determined what shade of red Coke Red was. And the student then realized that if he takes a little bit of pink and a little bit of our yellow and mix them in just the right ratios, we can recreate that color perfectly. Another thing you might want to do, you can toss in some cyan into the mix. And so yellow, magenta, and cyan makes black, which is how printers work. So we can mix those together and get a black ink, or maybe we could even consider which one of our colleagues did was that you can just print them in layers on top of each other to get a black color where you're, which is what you can see there on this butterfly pattern on the bottom. Now, another thing that we did, we were looking to make browns, and brown is surprisingly difficult to make as a color. And what we were interested in doing in this particular instance was to make electrochromic sunglasses. And so what we did here was we took a pair of sunglasses that we could just buy in the store, and we had determined what shade of brown they were. And then we looked at the color and looked at the spectrum, and we're able to see that, okay, if we take a little bit of our orange polymer and mix in a little bit of the blue, we're going to be able to recreate again that shade perfectly. And that's what we did here, which is what I'm showing here. On the bottom, we have this sort of purple brown colored lens. And we were able to switch this lens between a brown color and a clear state using just a small coin cell battery that was put into the back of the frame. And that's really another thing that I do want to highlight, which is what Carlos already showed with the little cute lemon battery, is that these really do not require much power at all to switch between the colored and the clear state. We can use a simple small coin cell battery. We can even use a little printed solar cell. So really not something that's going to be power intensive at all. And with that, I've been very fortunate over the last few years at Georgia Tech to meet a lot of very interesting people and a lot of creative people who have had amazing ideas about the kind of applications that you could use these for. And so certainly if any of you out there can think of a very cool application that you'd want something to switch from color to clear, please do send me an email or find me on LinkedIn. I'm always very excited to hear about new ideas and new applications that we haven't thought of yet. So with that, that was my little bit of science for today, and certainly after, I'm happy to answer any questions and concerns folks may have after we're done with the rest of the talks.
Thank you, Anna, very much. A very good introduction to colors in electrochromics. We'll go over to our next speaker, and also to just say it again that the questions to Anna will be shared after all the speakers have presented, and we will have a common question and answer session at the end. Our next speaker is John Coyne, the CEO of NXN-IP. John will talk about electrochromic polymers changing the way we see the world. And John is a serial entrepreneur with a background in complex systems architecture, where he holds multiple patents in software, electronics, and biosystems. And today, John will explain and give his view on business model and market applications for electroactive polymers. So over to you, John.
Thank you, Tommy. And as for everybody else, I hope you're all safe. I'm sequestered here in Southern California. My presentation is going to be oriented around the business issues and how we are getting this technology out into the marketplace. I'm going to share my screen with you now. Of course, I'm going to get to the very beginning. I wanted to say a couple of things before we get started. We work directly with Georgia Institute of Technology, and we are the sole licensee of the technologies that have been developed there. And not only do we have licenses for that, but we're also working with Georgia Tech on creating new intellectual assets that we will be patenting in the future. So our portfolio of patents is increasing. And so one of the things I wanted to do was to share with you a video that we created a little while ago that gives you an idea of some of the areas that this technology can be used for. You will see Anna again. You will see some of her colleagues, and this is going to give you a clue as to some of the projects we're working on. And then, because we can't name names, because we like to protect the intellectual assets of our customers. So for those of you who have exhausted your Netflix.
For years, we've fantasized about color-changing technology. From cars to screens to clothing and beyond, we've only dreamt of the possibilities. Until now, color on demand is now a reality.
My name is John Reynolds. I'm a professor of chemistry and biochemistry.
The Reynolds Group at Georgia Tech are recognized as some of the world's leading experts in electrochromic polymer materials science.
The ECP technology stands for electrochromic polymers that change color under an electrochemical stimulus. And in essence, we could capture any color of the rainbow.
So an electrochromic device actually consists of 5 different layers. We're going to have current passing through the cells, through all the different layers. And what's going to happen is that the molecules are going to change their shape or their conformation. And that's going to change how they interact with light. All right, so we're going to start off by coating our colorless polymers.
Creating a structure that includes a conductive surface to transport electricity, we apply the polymer components, the clear polymer, an electrolyte to conduct the electricity, and the color polymer.
So I'm going to show you how we switch an electrochromic device. And to do that, I have a laptop right here that's going to control something that we call a potentiostat. And what that is basically a battery. And that's going to hook two wires that I'm then going to connect to the electrochromic device. And once I hook it up to do that, I'm going to apply 1 volt. The device will switch between its color and its colorless state, where it's causing it to lose electrons and causing it to gain electrons as we apply 1 volt.
Think of the color like a ribbon. Looking at the ribbon full on, you see the color. But as we apply an electrical current, the molecules of the ribbon twist, and the color appears to get lighter as it moves into the invisible spectrum to become transparent. The color or clear state will remain until we apply the current again. This is unique in the industry, and only Chromatics can do it. With over a dozen global brands currently developing with Chromatics, the future is about to get a whole lot brighter. Chromatics, welcome to the color revolution.
She's like a rainbow.
So that's the introduction to the brand that we're calling this, Chromatics. As we move forward, our business model is that we are working with global leaders, I would say, in the retail and manufacturing spaces to basically change the way they think about using color in their products. We have exclusive licensing mechanisms. Generally speaking, that the people we work with will have an exclusive field of use license. Our revenue model is that we receive our revenues through license fees. At first, we had a model that was typical of many licensing fees that required our customers to audit and provide feedback on the products that they sold, and it was predicated on what those products were. Yanni at Ynvisible and I worked on a model that simplified the process by building our licenses into the supply chain and into the polymer itself. It simplifies the process, it makes it easier for customers to do business with us, and it certainly makes it easy for us to recognize revenue. We also do technology consulting because, as Carlos said, some people are pretty sophisticated about understanding this technology, others are just getting their feet wet. And we work with Ynvisible to develop prototypes and to develop technologies with our customers and help them get to the stage of realizing their vision into practical applications. And then we also engage in fundamental research. We have customers that we're working with who are fairly sophisticated and know that they want to create maybe some specialized molecules or specialized functions. I did see a question about the longevity of the materials and what it works on. I think Carlos and Anna covered that, but we're seeing tens of thousands of switches using our technology. And I do know that at some stage, Anna had a slide in her drawer that she pulled out after 2 years, and it worked instantaneously. And so we are looking at good, stable performance of our products. Now, when you saw the video, there was some fun ideas in there. We are working with some major global suppliers, and these are some of the areas that we're working on. Automotive interior and exterior components. You can imagine things, for instance, like color changing decals on cars, or even working at some stage on building color changing wraps so that the whole car can change. On eyewear and optics and frames, we are working diligently on a variety of areas in optics with some very large partners. General consumer products, I think Carlos covered that in his fun slide about all the different products that were in the household. Architectural interiors is something that we're particularly interested in because the architectural window space is pretty well covered by some very advanced companies. But we are working with a group at the moment to talk about the interiors of buildings, the color changing walls, for instance. And there's a lot more wall space in a building than there is exterior window space. In packaging security, you also saw that Ynvisible have been working on packaging products. Our colors can represent certain features for security. I think of chain of custody, for instance, is one of those applications where we can identify whether a product has been thrown out of the chain of custody or bypassed it, or whether a package has been dropped or not, so that you can tell before you even open it whether it's maybe damaged. Sportswear has become rather exciting because, as I will go through in a little bit in the next slides, we have been actually working with stretchable electronics. And we did a test very early for one of the companies we were going to partner with, and we've been successful in getting our polymers to change color on stretchable electronics. Mobile phones and devices, those you can imagine as what they are. In glass, we're looking at automotive glass and marine glass. You know, one of the features of our product is that once you change the color of our window, for instance, you won't need to use electricity to maintain the state. And that was particularly important in the marine applications we're looking at. In aviation, we're looking at aesthetics and safety features. In cosmetic products, we've had discussions with some of the cosmetic companies about color changing fingernails, for instance, which you may have seen in the movies in the past. And we're looking at color changing furniture, flexible displays, where instead of having active displays that you see ubiquitously everywhere, you will see reflective displays, more like color changing paper. And recently, we've made some discoveries that because of the absorption qualities of our polymers, we have some military applications that allow us to absorb a specific laser light, which has some strong implications in terms of our ability to enter a new market that we hadn't previously been looking at. And optical filtering is another area which is aligned to that military application, but this is where we can filter out specific light frequencies and build visual acuity, especially in optics. Now, we're going through a troubling time. A lot of the companies that I've been speaking to, some of which are trying to reserve their treasury so that they can withstand the downturn. Many of our customers, retail locations have shut down, their manufacturing plants have shut down. And some of these people are backing away to see how we recover from this economic calamity that we're going through. However, we have many others who are using this opportunity to ask themselves, how did they regain market share once this market turns around? How did they create products that people are going to want to buy that are not the same old Me Too products that were out there in the past? How do we actively encourage people to want to spend their money with us rather than someone else? Are our brands going to be important as they used to be in the past? And so we're working with a few of these innovators who are using this time to innovate and project into the future the ability to gain revenues that they might not have seen, and to certainly accelerate themselves into the marketplace. So they're going to come up with new categories of products. And we're investing with them, and they invest with us into the things they want. We're expanding our color palette. The little diagram that you see here, it gives you an idea of the color palette that is in existence at the moment, although we have broader characteristics in yellow. But we're going to be expanding to the full outer edges of the color gamut. We're building new molecules for specific types of applications. We're looking at new wavelength concepts because we want to be able to tune the wavelengths for specific applications. We're looking at new conductivity methods. As you may have seen in the video, we had a clear polymer that we used And that was basically used to absorb electrons. And some of Anna's colleagues have been working on the idea of highly dense ITO layers on the conductive materials that allow those electrons to be stored directly onto the surface, thus changing the architecture slightly and improving it by reducing at least one component in the development of the color changing material. We are looking at new materials, stretchable electronics, and new films. We are looking at thinner and thinner films because we want to see moldable films that can go onto surfaces and enter into the standard manufacturing processes that are well known. And we're looking at new barrier coatings because in automotive applications or other applications where the colors are going to be exposed to tough atmospheric conditions, or for instance in cars, rocks popping up and hitting material, we want to have coatings that have good ballistic characteristics, and we're investing in looking at those and working with customers that have and partners that have made some advances that look very promising for the future. So we continue to invest, and our customers continue to invest with us. And that's important for another reason. When we're working with our customers, confidentiality is a key factor. Many of our customers have ideas that they believe will give them a significant competitive advantage in the future. And for them to be able to do that work and conduct the research during the testing periods, we need to keep the intellectual property confidential. And so one of the key factors that we developed was the ability to build an academic firewall. As many of you may know, if you partner with an academic research organization and you sponsor research, much of that research will be published, and that may not be good for you from a competitive advantage point of view. But with us, we've developed a firewall capability. You can work with our academic resources, have access to the know-how, and share your know-how with our scientists, and fully protect your intellectual assets. Well, that leads to the access to our academic science and research. And you can also sponsor direct research into specific kind of chemistry that you would like to have worked on. If you know of a particular area you want to work in, we'll work with you, and you can engage in fundamental sponsored research with our academic resources. But also know that that development will be kept confidential.
Thanks a lot.
I'm just summarizing. It's a disruptive technology. We can create unfair advantage. We have a vibrant color palette. We have very fast switching, optical memory, which is important, world-leading academic corporate support. Our firewall and exclusive field of use licenses are still available. Thank you.
Thanks a lot, John, for explaining and giving us insights into the business model and market applications for electroactive polymers. So it's time to go over to Ashley Colley, our next speaker. He's a PhD and creative technologist at the University of Lapland, and also Ashley is the project manager for the Decochrome project that he will explain a bit about in his presentation. Ashley have a background in working in design for 20 years for Nokia, and Ashley is also co-founder of the Aura Ring that has been getting a lot of attention lately with the virus situation in the world. And Ashley will focus his presentation on design explorations in electrochromics and give examples of new potential application areas. So Ashley, over to you.
Yes, thank you. So I just share my screen. Okay, and thank you for Ynvisible for giving me the opportunity to speak. So I'll give first a short introduction to this Decachrome project. Then mostly I'll give some ideas about different applications that we've been looking at in the project. And then finally, I'll close by telling something about the work that we've been doing in the maker and do-it-yourself space. So firstly, the Decachrome project, it's a rather large European Union funded project, lasting 4 years with nearly 7 million budget. Here showing some of the visions that we started off the project with. So generally, I'd say that these are towards the area of calm computing. So rather than having to look at your smartphone display to get information on things, perhaps the information could be embedded in your surroundings. So here, one example showing, for example, near your front door, you could see the daily activity level of the members of your family. And then here on the right, perhaps in the bed headboard, there could be some dynamic printed graphic pattern that could show how well you and your partner have slept. So for example, here, when you glance across at your partner's headboard, you can see that perhaps they haven't slept so well. So these kind of ideas. So this was where we started off the project, really with these kind of visionary ideas. The project itself is really multidisciplinary. So it stretches right from chemistry, right through to design and pilots, and then everything really in between. So putting the chemistry together into electrochromic devices, and then also the enabling systems and elements around those, so largely printed electronics. Here today, I'll just talk about the design aspects of the project. So I'll just show some of the example prototypes that we've developed in the project so far. And all of the things that I present, they're fully functional prototypes, and they've been developed by various partners. So firstly, shoes. So now I think sensors in shoes are quite ubiquitous. So there's tens or even hundreds of companies working on sensors in shoes, but the output space of shoes is not really well covered. So one of the concepts that we produced was the idea to put an electrochromic display into a shoe and to really integrate it with the design of a shoe. So here we took an off-the-shelf shoe, designed some electrochromic displays and integrated them together with the electronics into the shoe. So the example use cases, for example, could be a shoe wear indicator here on the right to show when the shoe's worn out. Or on the toe and heel of the shoe to show how the runner's form is. Are they landing on the heel or toe of the shoe? These kind of ideas. So this was based on an off-the-shelf shoe. So the possibility to integrate the design was rather limited. So as a next step, we designed and built a shoe from scratch and integrated an electrochromic display. So here we linked it to a heart rate monitor. So when the wearer's heart rate goes above 100 beats per minute, then the flames illuminate on the side of the shoe. And I think this is a good example about approaching the design as a whole. So not just sticking a display onto an existing product, but really looking at how things can be designed from the beginning with electrochromic displays. Continuing with the theme of wearables, we looked at the possibility to integrate electrochromic displays into clothing. So here into an evening dress. It has electrochromic panels in the front and back and capacitive touch buttons on the shoulders. So the wearer can adjust the opacity of the neckline and the back panel depending on the context that it's been worn in. We've also looked at sports equipment and hand tools. So again, with sports equipment like tennis rackets, it's generally quite available to get sensor-equipped sports equipment, which sends the data to a smartphone. But here we looked at the possibility to actually integrate displays into the tennis racket itself. So the sportsman can immediately after they've played a few shots get some information on their performance. Then on the right, thinking about one of the most basic of human tools, an axe. How could we turn it into add some smartness to it? So here, integrating an electrochromic display. And this quite well demonstrates the possibility to fit the electrochromic display around the curved surface of the axe. So it really bends around the surface of the axe. Here, another prototype demonstrating the possibility for a little bit larger area electrochromic displays. So I think this is something which might be challenging to do with different technologies. So this is a kitchen scales, which has a fairly large scale display on the surface. Then, as was previously mentioned, just making the displays it alone isn't enough, so they really need to be integrated. So here's some examples of integration that we've done with the project partners. So an activity monitor, and here a demonstrator that integrates various printed electronic sensors with electrochromic displays. So that was just to give a flavour of some of the prototypes that we've been developing, just to see the potential for electrochromic displays in different areas. Another aspect of the project is engaging with the maker community. So it's possible to build these electrochromic displays similar to the ones that we've used in the examples I presented. Without special tools. So largely those displays we've built ourselves without any special environment or special tools, just on a kitchen table effectively. And the prototypes, as well as using spray coating or screen printing, they can be printed with a $150 inkjet printer. So this is the printer that we're currently using. And the quality is good enough for prototype level. So from design point of view, this is nice because it enables us to very rapidly prototype displays. So we can design a display, print it, and assemble it within 30 minutes. This kind of time scale. Linked with that, as part of the project, we've developed this toolkit for designers and artists. So this links with Ynvisible's ink kit, which is now available. So in here we have other materials lists, instructions, plugins for Adobe Illustrator, and also software to run the things. So using this together as part of the project, we've ran tens of workshops globally with maker and university communities. So here just some examples from the kind of thing. So I think the image at the top left is quite typical of how this has been run. So basically, people come along to the workshops, they design a display, we print it, and then they assemble it. So here showing some examples. So at the top right, for example, this shake it label, and then when the bottle is actually shaken, the display disappears. So these are kind of ideas that we've been developing in the workshops. Okay, so that was the end of my presentation. So thank you, everybody.
Thank you, Ashley. Thanks a lot to all the speakers today. We are running a bit over time now, but for those of you who would like to stay another 15 minutes, we will run the question and answer session right now. So please, if you have the time, stay on, and we'll go through a couple of your questions. And one of the first questions that came in here is actually to the question about the relationship between Ynvisible's Electrochromics and the relation to Georgia Tech and NXN technology. And maybe, Carlos, you could start out to explain technically how we can combine our technologies.
Yes, thank you for the question. This is this is a cooperative work we have established for some years already. We're basically we are covering a value chain. So we get from NXN-IP new electrochromic polymers that present this very vibrant and alternative colored materials that Anna has shown. And what we do on our end is we take those polymers that are basically powder and we convert them into solutions or formulations that can be coated or printed. And using our knowledge in printed electrochromic displays, we convert those materials into working displays that at the end will be inserted in a certain concept demonstrator for a final customer. And so it's very important here to remember that all these customers that John has mentioned, they don't care about components, but they care about a solution and a function. And that's what we all together, based on chemistry and then our know-how on prototyping, we can deliver these new concepts. And that's basically from the technical side, the workflow of these materials and how we cooperate.
Yeah, thanks a lot for that answer, Carlos, and explanation. Maybe John, or if we also have the CEO of Ynvisible, Jan-Mikael, attending here, could answer from a business perspective how we can work together with our different technologies and bring an offering to the market.
Yeah, so if I may, hi everyone, my name is Yanni. I'm the CEO of Ynvisible, and first of all, grateful for all of you attending this webinar, and thanks to our speakers, excellent job. To answer this question from a business model perspective, really, it's about bringing color into a wide range of different applications. NXN has a really impressive client list on a range of different applications and material sets. Ynvisible is focused on developing the printable electrochromic solutions that will go into different film substrates, plastics, papers, that can be deployed in these high volume printing processes. So what we do is we take those polymers, we formulate the printable inks and take them into these high volume manufacturable products. What John was talking about with these other areas of applications, there are so many other areas. Ynvisible, our aim is to be the leading supplier of printable electrochromic solutions from a design tool, inks, and quality control perspective. And it's for us, it's truly great to now have these new colors come into our palette. Hopefully that answers that side of the question.
Yes, thank you, Jan-Mikael. And I think we need to jump into another question, and this is perhaps a question that Anna and Carlos can help out with, and it's a question that is saying, what is the difference between printed electronics and electrochromics? So just to give a short answer to this, to explain to our audience.
Do you want to do that, Carlos?
Well, that's yes, printed electronics, it's a broader platform where basically companies and people are printing electronic components, or so to say, they are producing electronic components using printing techniques. Printed electrochromics is a subset of that platform. So what we talk today here is just one of the components that is enabled by printing. There are other printed electronic components like printed batteries, printed resistors, conductive traces. There's a multiple portfolio of electronic components that today can be printed using organic and inorganic materials.
I can hold up here an example of a device that we make at Ynvisible that is using the electrochromic display technology and some other printed conductors and so on to bring together with ordinary electronic components to create a product as well. So one more question then, and this is, I think, for you, Anna. Are the electroactive polymers printable with gravure or flexo technology?
I haven't done it myself, but they should be printable. It all has to do with making sure that when you make your ink, it has the right viscosity and that the solvent that your ink is in evaporate at the right rate. So there have been many demonstrations of similar types of molecules that have been printed. I'm gonna say it was gravure, but it could have been flexo as well. So it's just about, if you know how to make inks and you know what kind of additives to put in to make sure that you get the right viscosity properties, I don't see why they couldn't be printed that way.
Okay. One more question here that has come in is, are the electrochromic inks thermoformable after being printed in a flat polymer foil? And adding to that question is, are they able to maintain their properties with temperature? So maybe Carlos can start out and Anna to fill in.
I think Ashley has a very good experience, as is shown in the axe demonstrator. They have actually, maybe Ashley, if you can share a little bit of your experience on how you formed that display around the axe.
Yes, so basically we printed the electrochromic ink first and then heated the display around a former at I think maybe 100 degrees C in an oven, just to pre-shape it before we then assembled the display and fitted it to the axe.
Yeah, so thanks for that explanation. And I think this one is maybe towards Ynvisible and NXN. And this is like, how ready are the new colors for use in the market? You announced a health diagnostics customer last week. And what are you actually selling today? So have you anything to comment upon that? Maybe John, yes, please jump in.
I can't go into the details of what they're building because that comes under the proprietary nature of Market Advantage. But we are blending certain of our colors to create new hues and new tones for them to use in their product. I have to be vague. It'd be unfair of me not to, to go into any other disclosure. But this is for use on a product that sells in the millions on an annual basis.
And if I may add to that, the first part of that question was, what is the market readiness? So we are now at a point that we are receiving these polymers from NXN, and we're able to start developing these inks that go to these very tailored client-specific needs. So this is still early stage in the market, but it is very real and it is happening now.
Yeah, I would just like to add that when this came up, we went to Yanni first in Ynvisible because we know that they have the capability of producing the prototypes. And that's the most important part of the early stage is proof of concept. Can it do what it's purported to do? And Yanni's group makes that happen.
Yes, thanks, John. Great working with you guys. And the machine but behind Tommy there is where we'll do it in the millions.
Yes. Yeah, it's great to have that capability. One more questions to the speakers today, and it's this is I think the first question actually that came in, and it's, how do you see your position in the graphical non-emissive displays compared to, for example, e-ink? So maybe Carlos, Anna, Ashley, help out.
I can start by saying that, as I show in my slides, we are not competing directly with those technologies for certain applications. So I would say that the answer depends on the application we are targeting. There will be applications where we are honest and we say, it's better you go with an electrophoretic or something else. But if you, and based on the customers that have decided to keep and continue with us with Electrochromics, the main deciding factors were price of the technology, the transparency, and the form factor that is possible to achieve with Electrochromics, as well with printability, and also the low voltage that is required. So we need to remember that these electrochromic devices can be switched with something between 1 volt to up to 3 volts. 3 volts is the maximum that is required. And in addition, we offer something that no other display technology can offer, which is this irreversible switch. And when we fall in those security sensitive applications where the information has to be kept, even if the battery has died or someone has tried to corrupt the sensor, then you need an irreversible visual indicator, and that's quite unique of Electrochromics at this moment.
And Tommy, if I may add a few words to this, alluding to Carlos's presentation. The electrophoretic type displays, they come more from the application spaces of conventional electronic displays and expanding that domain. We are really taking this a step further towards the printed world. All these, it's an $800 billion industry, the printing industry, with a wide range of applications. There's a lot of blue ocean for this type of new, simple electronic display functionality that can be produced in high volumes in multiple print houses around the planet. This is being built to be a scalable technology produced in print houses around the world.
So,
Tommy,
yeah, sure, yeah.
I think the principal difference is also the color palette portfolio. You know, I worked with the inventor of the e-ink many years ago when I was doing some electronics work. And to my understanding, I think between us all, we'll be one of the few groups that can print these displays in full color.
Yeah, so thanks a lot to our speakers for answering these questions. And I would like to just say thank you to the audience also, and to all of you who have been participating and contributing with questions today. And thanks maybe to Ashley's work from a design perspective. We have been given a lot of insights of the needs for design tools for designers to develop new applications for electrochromics and electroactive polymers. And so to meet that demand, we have also taken out some kits, so everybody could start out and trying out the electroactive polymers and electrochromics, and they are available on our website and easy to order. So go ahead and try out yourself. We, as I stated in the beginning, this is the first seminar that we give in a series of seminars under the hashtag of Things Alive. So keep watching our social media for postings of the next seminar. During next week, we will have set the date for the next seminar that will be focusing on RFID and logistics applications using the display technology. So I think that's all for today, and thanks a lot for listening and taking part of our presentations today.
Tommy, sorry to interrupt.
Yes.
There's been roughly 30 questions coming in. Unfortunately, we're not able to answer all of those now. We do want to engage in dialogue with you, so do get in touch. We're happy to answer these.
Yes, and please take the survey. And there you have the chance to fill in your questions so we can go get them and answer. So thanks a lot for your contribution to the audience, and special thanks to today's speakers. So, bye-bye.
Thank you all. Stay safe.